Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. So here is a video on lecture video and sample problem videos on internal forces and moments. This is in preparation to the construction of the shear, force, and bending moment diagrams, as well as the sketching of the elastic curve. So it is important that the free body diagram is correctly made, labeling all the internal forces and writing equations of statics to solve for these internal forces. And finally, and hopefully, you are able to prepare for problems where you can solve by your own and prepare for your quizzes and exams. I hope that this video will help you in your preparations as civil engineering students and allied engineering students in some aspect. So I hope so. So before analyzing beams, it is important to have sign conventions in preparation for the construction of the shear force and bending moment diagrams. And it is important to emphasize these sign conventions. Also, we define a beam as a slender member whose whose loadings are transverse or perpendicular to the axis of the slender bar. Now, if there are loadings that are inclined, so there will be uh, components of that external loadings which will cause normal force or axial force, but in general that axial force is negligible because the cross section is big, and what matters would be the shear and the bending moment, although it is part of the problem maybe in the future. So that's it. So for the sign convention, we adapt the following sign conventions. This figure is taken from the book by Pitel and Cuselaas. And so for external loads, the positive, don't mind for the negative anymore. It's just the opposite. So we have clockwise, couple, downward, everything will be downward. So that's the positive for the external loadings. For the shear force, at the left section should be upward and at the right section should be downward. In other words, we have a positive shear if that member in particular will cause uh, clockwise moment clockwise moment. So if it is counterclockwise, it's negative. But let's focus or concentrate on the positive sign convention for loadings. Everything will be downward, and for the couples clockwise. And for the shear force here, so again at the left it should be upward, and I will always emphasize this in the problem solving later. And in at the right section downward, that's positive shear. Or if it causes clockwise rotation of the member. Then for the bending moment, it should produce this bending, which is smiley face bending. So at the left, so that the bending curvature will be of this form. At the left, the couple or the moment should be clockwise, and at the right section should be counterclockwise. So these are positive sign conventions. As I said, let's focus on this. So for the next batch of problems to be solved, it will be about beams. Level 26, this is a very common problem, and I want you to remember the results of this problem. For the beam shown, derive expressions for shear and moment and draw shear force and bending moment diagrams. Neglect the weight of the beam. So here is the given figure. By symmetry, the vertical reaction at A and B will be equal. The total load is the area of the loading, WOL. So its vertical reaction should be WOL over 2. Horizontal reaction at A is 0 as shown. So for the shear and moment equations, so we just isolate one part and we'll call the distance from left as x. So imagine shear is downward and moment is counterclockwise here. So this is the figure. We have the shear and the moment in that positive directions. So therefore, shear is WOL over 2 minus the area of this loading WOX. So WOL over 2 minus WOX. That's the shear equation in this section. For the moment, it is WOL over 2 times x minus the moment of the load, which is WOX, the area, WOX acting at the centroid of the rectangle, then the moment arm x over 2. So WOL over 2 times x minus WOX times x over 2. Simplifying, moment is WOLX over 2 minus WO over 2x squared. So that's it for this equation. Then for the construction of shear and moment diagram, when x is 0, this is 0, then shear is WOL over 2 initially. So that's WOL over 2. And when x is L over 2, this is 0, so it crosses here. This is a straight line graph with intercept WOL over 2 from construction of curves, and it is sloping down because of this coefficient of x, which is negative. So that's why if you differentiate this equation, derivative of shear with respect to x, the answer is negative WO. So that gives us the idea that the slope of the curve on the shear diagram corresponds to the loading intensity of the loading, which is WO, negative of WO. So because this is 0 degree, then in the shear diagram it is first degree or a straight line, x to the 1. So again, the derivative of shear is the load, and the derivative of the shear is the slope of the shear curve, and it is interpreted as the negative of the intensity of the load above. So it is 0 at the center, then if you substitute L over 2, 1 half WOL minus WOL. If you substitute L here, then it is negative WOL here, then it closes. So that's the shear diagram. The maximum shear, absolute shear, is WOL over 2, and it occurs either just to the right or just to the left of the support. So remember that. And remember also that the slope of this curve is the negative of the intensity of the load above, or the negative of WO. And if you want to check the slope, then check it. Then for moment, when x is 0, moment is 0. You may shade, you may not. There's no agreement that the shear and moment diagram should be shaded. It is only for looking at the shear diagram look attractive. So that's why it's shaded. When x is 0, moment is 0. When x is L over 2, or when x is L over 2, WOL square over 4 minus WOL square over 8. So WL square over 8, the maximum moment. And take note that the maximum moment occurs where shear is 0. So when shear is 0, moment is maximum. Take note of that. The tangent here is horizontal. And this is WOL square over 8, the maximum moment in a beam loaded, simply supported beam or end supported beam loaded with uniformly distributed load of WO. And we may shade it. So that's it. Now, That's it. So if we differentiate this moment equation, it corresponds to the slope of the tangent to the moment curve. So if we differentiate this with respect to x, it is WOL over 2 minus WOX, which is the shear. Take note, if we differentiate moment with respect to x, it is the shear. So take note of that relationship. That is very important later on in constructing shear moment diagrams. Level 27, for the beam shown, derive expressions for shear and moment and draw the shear force and bending moment diagrams. Neglect the weight of the beam. So here is the given beam. It is loaded with linearly varying load from 0 at the left support to maximum WO at the right support. So we will call the reactions AY at the left, AX is 0, definitely RB. Summation moment about B equals 0, so the equivalent loading is the area of this loading, which is 1/2 L times WO, WOL over 2, and its distance from the right is L over 3, distance from the left 2/3 of L. So summation moment about B equals 0, AYL times L, AY times L minus WOL over 2 times L over 3 equals 0. So AY is equal to WOL over 6. So likewise, if you sum up moments about B equals 0, so it is WOL over 3. I will leave that to you. So let's have the shear and moment equation, but before that, at the distance x from A, we will call the intensity of the load as W, and we derive W by similar triangles. W as to x equals WO as to L. So that means W is WOX over L. Then let's isolate WOL over 6. Summation versus y plus RB equals WOL over 2. So that's why RB is WOL over 3. So for the shear and moment equations, this is the positive shear, positive moment. Summation versus vertical equals 0. So shear equals WOL over 6 minus the area of this triangle, 1/2 x WOX over L. So WOL over 6 minus 1/2 x WOX over L. Simplifying, the shear equation is WOL over 6 minus WOX squared over 2L. So that's the shear equation. For the moment equation, it is WOL over 6 times x, then minus this area, WOX squared over 2L, and that distance is x over 3. So times x over 3. Simplifying, moment is WOL over 6x minus WOX cubed over 6L. Differentiating this equation, let's show that it is the shear. So WOL over 6 minus WO3 x squared over 6L, so it reduces to WOX squared over 2L. Then we equate it to 0 because this is the slope of the tangent to the moment diagram, moment curve. And notice that this equation is the shear equation. So that's why the slope of the tangent to the moment curve is equal to the ordinate shear, correspondingly shear above. So take note of that relationship. And remember earlier that the derivative of shear with respect to x is the intensity of the loading. So if you differentiate this, this is equal to WOX over L, the intensity of the loading W. So take note of that relationship. The reason why we equate this to 0 because we want to find the maximum moment. So solving for x here, x is, you can cancel WO, so 2L over 6 is L over 3. 2L squared over 6 is L squared over 3. Square root, extracting the square root, so x is L over square root of 3. That's the location where moment is maximum. And the maximum moment is obtained by substituting the value of x L over 3 in this formula here, in this moment equation. And you will arrive at square root of 3 over 27 WO L square. So it will be shown in the moment diagram also. So shear when x is 0, WOL over 6. So WOL over 6. Then because the sign of the second degree term is negative, that means the curve is concave downward from 0 to L. So just draw a curve that is concave downward and pass it through points where we substitute values, like for example when x is L over square root of 3, we'll find that shear is 0 here. That's 0. When x is L, 16 WO L minus WO L over 2. So that's negative WO L over 3. And it closes because RB is WO L over 3. So that's the shear diagram. For the moment diagram, take note when shear is 0, moment is maximum. So the slope is initially 0. Initially WOL over 6 for the slope in the moment curve. Remember, the slope of the tangent to the moment curve is the shear. So if the shear is 0, the moment is maximum here, the tangent is horizontal because the slope of the tangent to the moment diagram corresponds to the shear above. So the shear is 0 here, so the slope here is horizontal or 0 slope. And the maximum moment is square root of 3 over 27 WOL square as shown in the figure. Then when x is L, here we already plotted this. When x is L in this moment equation, then moment is 0. You just substitute L here. You will find that moment is 0. So that's the moment diagram. Maximum moment, it occurs at L over square root of 3 from the left support. So that's it for this part. Level 28. For the beam shown, derive expressions for shear V and moment M and draw the shear force and bending moment diagrams. Neglect the weight of the beam. So here's the given figure. Let's solve for AY. AY is just AY, then AX is 0, then we have R sub C. So summation moment about C equals 0, AY times 6 minus 36 times 3 times, it is acting at the centroid. So 1.5 from C, half of 3 is 1.5, so times 1.5 equals 0. So AY is equal to 27 kilonewtons. Likewise, summation moment about A equals 0, R sub C times 6 minus 36 times 3, 1.5 plus 3 is 4.5 equals 0, so R sub C is 81 kilonewtons. So for the construction of the shear moment diagram, let's prepare it. So shear diagram in kilonewtons, then moment in kilonewton meter. So at the distance x, this is the free body diagram. So we have shear positive downward and moment AB counterclockwise. Summation versus y equals 0. So shear AB is 27, constant for 0 less than x less than 3 in general. So for the next section, by the way, for moment AB is 27 times x. So that's the equation, 0 less than equal to x less than equal to 3 meters. Then for the next section here, there are 2 segments of the beam where loading changes. So another change in loading here. So this is the last section. And we isolate it here. So we have shear downward, positive, then moment BC. Summation versus y equals 0. So shear BC is 27. This distance is x minus 3 shown. So 27 minus 36 times quantity x minus 3. Simplifying, or we may simplify that or leave that way. For moment BC, it is 27 times x minus the area here is 36 times x minus 3. The moment arm is quantity x minus 3 over 2. So that's why 36 over 2 is 18. Then we have x minus 3 square. Again, moment BC, 27 times x minus this, the moment of this loading. The load, equivalent load is 36 times x minus 3. The moment arm is x minus 3 over 2. So 36 over 2, 18. Then we have x minus 3 quantity square. Applicable for 3 less than x less than 6 meters. So up to 6 meters. So let's now plot first 27 from 0 to 3. Constant. Then just to the right, shear is still 27. Then minus, when x is 6, substitute 6 here, 27 minus 36 times 3, that would be y3 because 6 minus 3, negative 81, and closes. Then let's shade the figure. By the way, this distance can be found by similar triangles. Call this x1 as to 27 equals 3 minus x1 as to 81. Then you can find this distance. The easiest way to find this distance is the shear 27, then divide it by the load 36, intensity of the load. 27 over 36 is, you will find that distance. So for moment, when x is 0, we have negative moment AB rather. When x is 0, 27 times 0 is 0. Then when x is 3, 27 times 3 is 81. This is also 81 when x is 3. Because this is 0, then 27 times 3 is 81. So it is continuous. Then when x is, so let's find this first. By similar triangles, x1 as to 27 equals 3 minus x1 as to 81. You can find that. But the easiest way is shear 27 divided by intensity of the load 36. And that is equal to 3.75. We just set this shear equation BC, it is for BC, to 0. Then you will find x is 3.75. But that 3.75 begins at the origin here at the left. 3.75. So that means this is 0.75. So if that is 3.75, this is 0.75. And 0.75 is 27 over 36, as mentioned earlier, the SHEAR way. So that's why the ordinate here is when x is 3.75, where is that? Substitute in BC. 27 times 3.75 minus 18 times 0.75 square. 3.75 minus 3 is 0.75 squares. So you'll get 91.125. Then finally, when x is 6, substitute here 27 times 6 minus 18 times quantity 6 minus 3 square. You will find that it is 0. So that's it. And the curve is concave downward because the second degree term has negative sign again. So it is concave downward. If you differentiate this with respect to x, remember it is shear. And if you describe the ordinate of the shear, it is from positive and it decreases until constantly first degree to second degree until it is negative 81. So the slope is beginning here is 27. Here 27 the slope because the ordinate is 27. Then 0 when shear is 0 horizontal. Then the slope here is negative 81. So that's negative 81. And the reason why it is concave downward like that, it's because the ordinate of shear decreases from positive to negative. So slope also decreases from positive, then 0, then negative, increasing. So that's the description of the tangent to the moment curve. So let's have the next problem. Level 29, for the beam shown, derive expressions for shear and moment and draw the shear force and bending moment diagrams. Neglect the weight of the beam. So here is the given figure. So first, let's solve for AY. AX is 0. Then we have R sub C. Summation moment C equals 0. AY times 7.5 plus 60 minus 40 times 4.5 equals 0. Solving for AY is 16 kilonewtons. Likewise, summation moments about A equals 0. R sub C times 7.5 minus 60 minus 40 times 3 equals 0. So R sub C is 24 kilonewtons. 16 plus 24, 40 minus 40 equals 0. So it checks. Then for the shear moment equations, so we section this portion and let's have the isolated part, or we just imagine shear AB equals 16 for 0 less than equal to x less than equal to 3. Then moment is 16 times x, so we just sum up. You just take moment about that section and the distance is x, so 16 times x. Moment AB for 0 less than x less than 3. Now for this section here, shear is summation versus y. Remember, downward shear, positive. So 16 minus 40, that's the equation. 16 minus 40 for shear BC is negative 24 kilonewtons. For 3 less than x less than 7.5, applicability. Then for moment, we just take moment here. Imagine shear downward, moment counterclockwise. So moment is 16 times x minus 40 times this distance, moment arm is x minus 3. So moment BC 16 times x minus 40 times x minus 3, then plus 60. Simplifying, moment BC is negative 24x plus 180 for 3 less than equal to x less than equal to 7.5. So we have completed the equations. We can now plot. When x is 0, shear is 16. When x is 3, shear is still 16. So we have horizontal curve. The value of shear is 16 up to here. When x is 3 just to the right, so shear AB is no longer applicable. We proceed to shear BC. It is negative 24. So negative 24 constant. Even when x is 7.5, the shear is negative 24. So that's the shear diagram. For the moment diagram, when x is 0, moment AB is 0, 16 times 0. When x is 3, 16 times 3, 48. So we have 48 there. Then when x is 3 just to the right, this is 0. So 16 times 3, 48 plus 60, 108. So it changes abruptly to 108. So just substitute in moment BC, x is 3.0001. So this is 0, 16 times 3 plus 60 is 108, shown. When x is, so after BC, so when x is, you may substitute here, when x is 3, negative 24 times 3 plus 180 is still 108. When x is 7.5, negative 24 times 7.5 plus 180 is 0. It is a straight line because this is a line with negative slope. This is constant, so horizontal. Constant, so horizontal. Line with slope 16 and positive. So the slope of this moment curve is 16 because the ordinate of the shear diagram is 16, constant. So that's why this is also constant. The slope is 16. Then here, from 108 to 0, the slope is negative 24. So that's 0. This is the moment diagram. Then lastly, for level 30 problem, for the beam shown, derive expressions for shear and moment and draw the shear force and bending moment diagrams. Neglect the weight of the beam. So here is the given figure. Actually, we don't need to solve for the reactions at C. We simply section the beam. There are two sections, AB and BC, then isolate the left portion. So anyway, let's just solve for Cy. Cy is 1800 times 2.4. Cx is 0. Then moment is clockwise, so that's negative supposedly. But let's just consider the magnitude and the direction is there. Summation for Cy equals 0. Cy minus 1800 times 2.4 equals 0. So C sub y is equal to 4320 newtons. Then summation moment about C equals 0. M sub C minus 1800 times 2.4. Moment arm is 1.2 plus 1.8 or 3. Then equals 0. So M sub C is equal to 12960 Newton meter. We're now ready to establish shear and moment equations per segment. First, on section AB at distance x. So we imagine we have shear here. So shear AB is negative 1800 times x. That is for 0 less than equal to x less than equal to 2.4. But to be safe, 0 less than x less than 2.4. The shear curve is continuous in this case. Then moment AB, so plus, it is negative plus 1800 times x, moment arm x over 2. So moment AB is negative 900 x squared for 0 less than x less than 2.4. Again, negative 900 x is moment counterclockwise. We imagine this distance is x up to here. Minus 1800 times x, that's the load, which acts at the centroid of the rectangle of length x, moment arm x over 2. So that's why it becomes negative 900 x squared. And in this section, so shear is simply negative 1800 times 2.4. And it is constant. So shear in BC is negative 4020 newtons for 2.4 meters less than equal to x less than equal to 4.2. And it is given as shown. So it begins with 0, then shear when x is 0, this is 0, when x is 2.4, so it is negative 4020. It is straight line because this represents a line with negative slope. The slope of this curve is intensity of loading above negative 1800. So if you differentiate this with respect to x, it is negative 1800. Remember, the slope of the shear curve is the intensity of the loading above. If there's no loading, then it is 0 or horizontal. Just like here, shear in BC is negative 4020. So it will just be continuous like that. So that's the shear diagram. For moment BC, we simply sum up moment here. Moment BC is negative 1800 times 2.4. That's the load, equivalent loading acting at the centroid. Its moment arm, this distance here is x minus 1.2 because this is 1.2 half of 2.4. So that's why we have moment arm x minus 1.2. Simplifying, moment BC is negative 4020x plus 5184 for 2.4 meters less than equal to x less than equal to 4.2. So we will now plot first moment AB, negative 900 x squared. Negative 900 times 0 square is 0. Begins with 0. Then when x is 2.4, negative 900 times 2.4 square, the curve is second degree, it is concave downward like that because the coefficient of the second degree term is negative, so concave downward. The value is negative 900 times 2.4 square, and that is equal to negative 5184. Again, substitute here negative 900 times 2.4 square, negative 5184. For BC, when x is 2.4, you can evaluate it is negative 5184 also. When x is 4.2, negative 4020 times 4.2 plus 5184. So it is concave downward again. It is a straight line, sorry, because this represents a straight line with negative slope. And the value here is negative 12,960 because this is 12,960, so it's correct. So that's the moment diagram, and I hope that you